So now that we got our game manager and our player movement set up, why don't we go ahead and build our playing field, the boundaries of our game. In this game, we're going to create boundaries that the player cannot move past. So we're also going to develop a functionality to them that shrinks the boundaries if a penalty occurs, such as missing an object or getting hit by an object in future gameplay in our game. So we need to create something that shrinks our playing field for us. All right, so we're going to do that inside of our game manager. But first, we actually physically have to build our playing field here. So what I'm going to do is I'm going to create an empty game object. I'm going to reset its values. I want to say, call this boundaries, like so. There we go. And so why don't I create just some regular old primitives here. All right, so let's see. I'm going to set their position and scale separately. But first, why don't I go ahead and build this out and call them right that way, and then parent my cubes underneath my boundaries game object. And I'm going to go ahead and set up the position and scale of my right boundary here. So I want to make a square arena. So I'm going to position my cube over to the right, like so. And I'm going to scale it 20 units in the Z axis. So we've created a right wall. And why don't I go ahead and, let's rotate. Why don't I go ahead and scale up in the Y direction, like so. So there's my right wall. And I'm going to do this for all of my boundaries here. All right. So I'll duplicate my right. And why don't I call this left? And we're simply going to do a -10. And then for my top and bottom, let's make our top one right quick. I'm going to go ahead and reset the X position. I'm going to rotate it 90 in the Y direction. This is very important to rotate it instead of recalculate the different scale values. This will be a nice way to keep track of the position and scale in later bits of code. But I am going to adjust its Z value. That way it puts it up top. And you're kind of noticing a theme. We're kind of keeping our values very similar to one another. And all I got to do for bottom is do a -10. And now I've created a nice square arena. All right. So there's a few more things we need to do. We need to set tags for them. So I'm going to select all of my boundaries here. Just shift click all of them. And why don't I make a boundary tag so I can easily access these inside my code. So boundary. All right. After I've made my tag, I'm going to go ahead and assign it to that. So now my top, bottom, left, and right all have the same boundary tag. And now I need to start paying attention to the aspect ratio that I want my game to be presented in. So a lot of different aspect ratios are given to us. This is like old school TVs. And here's our widescreen TV. We got to make sure, I'm going to go ahead and work in 16:9 aspect ratio. And I'm going to set up my camera so it's encompassed. And you know what? Actually, I'm going to take my camera and I'm going to set it to orthographic, so we don't get that perspective skewing of my walls. You'll notice now in my game view over here, we can't even see my walls anymore. So I'm going to have to increase the size of my orthographic projection range to something, let's say, about 12. That gives us plenty of room to look straight down on my playing field. And I'm noticing something else. My corners have like these little gaps in them. You can either leave them in or you can change them. It doesn't matter. So I'm just going to say 21 for the top and bottom Z scale. Just changing the scale transform in the Z axis for my top and bottom to an extra unit. And that'll close up the gaps within my border here. All right. So we've done all that. Now we need to be able to get at these different cube boundaries inside of my code here. So we're going to go to our scripts, and we're going to live inside of our game manager class for pretty much all of this video here. The first order of business is to make our boundary cubes accessible in our code. So we need to be able to get at these boundaries inside of our code so we can start moving them and seeing where they exactly lie. So I'm going to do this by first starting to create a public game object, and we're going to make an array. So we're going to put straight brackets, and we're going to call this array boundaries. All right. So now we have an array or a list, an empty list, where we can populate all of my boundaries so we can keep track of them all. So now we need to, in our awake function here, we need to populate my empty boundaries array by saying boundaries equals, and here's where our tags are going to come in handy, game object dot find game objects plural. Don't forget that little S right there with tag, and in parentheses and in quotations we're going to type boundary. Let's close out that quotation mark and hit semicolon, and we're out. I'm going to save and compile. So let's select my game manager. We can see now that I have a boundaries array right here of size 0. When I press play, it should populate with the bottom, top, left, and right, all of my boundaries right here, as you can see. So now that I have an array where I can get at each one of my cube boundaries, I can actually start manipulating their size and scale. So inside of my game manager script, I'm going to make a new public function that will shrink our boundary for us. So let's say public void shrink boundary. Empty parentheses, we're not going to pass any values in, and make sure you make your brackets. So this function is going to be responsible for growing or shrinking, in this case shrinking. We will be able to grow it maybe if we wanted to add a power up that grew it back up, but we're going to focus on just shrinking it right now. Okay, so within this shrink boundary, we need to make a for loop that accesses each cube boundary within our boundaries array, because we want to basically apply a shrink to all, or a shrink and a move to all 4 game objects within our boundaries array. So why don't we say for int I equals 0, and we're going to say I is less than the name of our array dot length. So it'll basically say, okay, we're going to loop through this array, this for loop. We're going to loop through this loop only the amount of times as there are objects in my array there, and we're going to increment our counter each time. All right, so let's make our brackets. All right, so we got our for loop made. Now we need to have some if statements that check which boundary we're actually looking at and what to do to each boundary, because we're going to have to be doing different things to each boundary. You know, the top boundary here is going to have to move down in the x axis here, while the right boundary has to move, or actually, yeah, it's moving in the z axis, while our right boundary has to move in the x axis. And they all have to scale down as well too, so they keep this perfect square going. So I'm going to undo all those changes. So now we need to basically say, okay, which boundary am I currently looking at? We need to make those distinctions. So we're going to do that with a bunch of if statements. So we're going to say if boundaries, and then since we're in a for loop, we can access our objects in our array pretty easily using our counter variable here. So the first time through the loop, our counter variable equals 0, which just so happens to point to the very first element. If I open this up and play, the very first element in our boundaries away, which is our bottom cube. So the first time through the array, our boundaries equals boundaries bracket 0, and we're looking at our bottom. And this will do that for each single object in our array. So it's really nice that way. So we're going to say if this boundary that we're currently looking at in my if statement, and we're going to check the positions of the transforms, the positional transforms of each cube. If you'll notice, I'm going to go through and select each one of my boundary cubes. They all have a unique position in our X or Z axis. So our right cube has a positive 10 value, while our left cube has a negative 10 value. Our top cube right here has a positive 10 in the Z, and our bottom has a negative 10 in the Z. So that's how we'll be able to say which cube is which inside of our code. We're just going to look at their positions. So we're going to make an if statement for each one of those different conditions we just talked about. So we're going to say if this boundary in particular is transform.position.x is less than 0, then that's going to be our right boundary. So I'm going to make a special comment about that right there. So why is that our right boundary? Well, what we're saying is if this particular boundary that we're looking at in our for loop that's going through our boundaries array, if its position is greater than 0, all right, and our right boundary in the X 10 is greater than 0, so we must be talking about our right boundary. So we're going to leave the body of code empty. We're going to make sure we get an if statement for each and every single one of these boundaries here. Then we're going to do we're going to continue our if statements with an else if. And you know what? I'm just going to copy this line of code right here. Let me zoom in a little bit. I'm going to copy this line of code right here and just paste it because we really just have to do a few tweaks to every single one. So if I want to get the left one, all I really have to do is say, okay, if this X position is less than 0, such as maybe negative 10, then that's the left side. All right. And then I simply just make my brackets. And you know what? I'm going to copy this whole else if. And I'm going to paste it a few more times. And now we're going to start looking at the Z axis, the potential Z axis of my boundaries here. So if my Z is greater than 0, then that's obviously my top boundary. And then I'm going to change this position X to position Z. And this is obviously my bottom boundary. So these four if statements here, they're checking the position in the X and seeing if it's greater than or less than 0. And then these bottom two are checking the position in my Z. And these will catch the top and bottom boundaries. So now we have a nice little logic set up. Every time we go through my for loop, I'm testing each one of my boundaries here, and each one of my boundaries are definitely going to fall under one of these four nested if statements we have going on right here. So now that I can access and look at each one of my boundaries to determine which one I'm currently need to solve for in terms of repositioning its position and scaling it down, I need to get set up for actually doing those commands. So I'm going to have to make some variables starting out. All right. So what variables am I going to have to make? Let's see. Well, before I can move the position or change the scale, I'm going to have a placeholder variable that equals the current scale or current position of each of my boundary cubes so I can actually update them. So just take me at face value there. So what I'm going to say is public, or I'm going to let's make it private. Let's say vector3. We're going to create a vector3 variable here. We're going to call it current position and current scale, like so. So these are going to be temporary placeholders that I can plug the values of the current boundary cube that I'm looking at, maybe like the current position or current scale of my right boundary here. That'll make updating its value a lot easier. And then I actually need to, this is going to be a very important variable here for determining the balance of how much our playing field shrinks. We're going to make a float value that says, okay, we're going to shrink our boundary by this amount. So I want to say boundary amount, like so. All right, so these three variables right here will be very important when actually shrinking our playing field here. So what we're going to do now is I could just go ahead and put all the code in each one of these if statements, but I'm already going to recognize, remember with our player mover, I had to write all this code like 4 different times for each if statement. But in the end, I ended up making a function that cut down on a lot of that. So I'm going to go ahead and make a function for these if statements because I know I'm going to be repeating the same lines of code because the commands I'm going to do for each boundary are going to be very similar. So I'm going to go ahead and make a brand new function. And we're going to call this void shrink. All right. And it's not going to be public because we're not going to access this function outside of my game manager. This function is just going to be my shrink boundaries little buddy. He's only really going to work for shrink boundary here. So public void shrink boundary will be accessed in any script, such as, our player mover. And just a regular void shrink will only be accessible in my game manager. And we got to figure out what is unique for each cube adjustment. Like what things are we going to adjust uniquely for each one? So we got to be able to say, okay, what actually are we going to shrink in this game, this function here? So we got to pass in the actual game object of the boundary we're actually looking at. So we got to pass in if it's the right game object or the left game object or the top or the bottom game objects. So when I want to go ahead and say shrink, and then I'm going to pass in boundaries. So that'll be the first parameter I need to pass in. So in my shrink function down here, I need to say game object, capital G, and then why don't we call this param for parameter, param boundary. All right. So whenever I call my shrink function, I'm going to pass in the actual boundary that we're solving for currently within our for loop. So if I'm currently going through the for loop and I'm looking at my my right boundary, then it's going to see that its x position is greater than 0. Then it's going to call the shrink function, and it's going to actually pass in the right boundary game object within my array, and it'll get passed in right here. So now I have this new local variable called param boundary to use within this little function down here. So I'm going to go ahead and reset that up. All right, what else do we need to pass in to the shrink function? Well, we need to pass in the position that we need to move it in, the actual vector that we need to move our boundaries in. So we're going to do that by saying we're going to create a new vector 3. And then a vector 3 is basically just a variable that holds x, y, and z coordinates, or values rather, x, y, and z float values. So what we're going to have to do is let's just solve for our right boundary now, because this new vector 3, when we call our shrink function, is going to be different for each one of my if statements here. So let's just solve for my right boundary right now. So what we're going to say is we're going to pass in a new vector 3 that updates the position of this boundary wall. And since it's the right wall right here, what we want to do is we want to update its x position, and we want to bring in that x position in. We want to almost make our x position less. If we added to it, then we'd start to see my wall go the opposite direction. We want it to come in and shrink. So currently it's 10. So what we can do, since we've made this public float boundary amount, this is what we're going to pass in when we create this new vector 3 that'll update the position of my wall. So we'll say new vector 3, and then we're going to say boundary amount for my x value. So you'll notice vector 3 has an x, y, and z variable. And then over here, we'll just say 0.0f, 0.0f for my z. And then we'll close down those parentheses. And that looks to be about what we need to pass in. So we want to pass in this new vector 3 that'll update only the x position of my boundary wall here. So that means we have to make a new parameter down at the bottom here, and it'll be a vector 3 parameter, and let's call it param vector 3. All right. So we're passing in our actual game object to param boundary, And our new position, we want to update our game object to this param vector 3 down here. Very generic variable names, but they only exist within this shrink function right here. So I think we'll be able to get away with them. All right, so what kind of code do we need to put in here now? Well, the first 2 lines of code we need to do, we need to update our current position equals our param boundary dot transform dot position. So now you can see why this current pos is so important, because we need to have a value that can hold just the current position of whatever boundary we're passing in to our shrink function here. And then we'll do the same for current scale equals param boundary dot transform dot local scale, like so. So now that we have these placeholder variables right here, or variables, I guess they are pretty valuable to this function, we can actually start updating the position and scale of my current boundary that we're looking at. And right now we're just working with my right boundary, for instance. So let's just keep in that mindset. And we're going to say param boundary dot transform dot position equals the current position it's in minus my param vector 3 that I passed in right here. So we're going to take the current position, which is 10, 0, 0. Let's look at my right boundary again. My position, my vector 3 for my position for my right boundary is 10, 0, 0. Now we're going to subtract this new vector 3 from that. So if our boundary amount is, I don't know, 1, then we're going to subtract 1 from the x, 0 from the y, and 0 from the z. And that'll effectively move this right boundary over 1 unit, like so, 9, 0, 0. So that's how we're going to update our position. It's going to subtract one vector from another. And then we need to do the same for scale. So we'll say param boundary dot transform dot local scale equals current scale minus, and then since this is going to be interesting, we're not passing in any new variable for our scale. Since all of our boundaries are scaled the exact same in the z-axis here, they're all 20 in the z-axis, or 21 depending on what if it's top or bottom. Then that makes this line of code easier. We're going to do the same thing. We'll be able to do the same command for each of our boundary walls here. So we can just simply say equals, and then we can do the new vector 3 down here instead of passing it in as a parameter. And then we're going to say 0.0f because we don't want to subtract in the x, and we don't want to subtract in the y scale. What we want to focus on is subtracting in the z scale. So what we need to say is boundary amount, and then times 2, because our scale, if I select my scale is twice the value of my position. That's why this cube is really handy. So my boundary amount that I'm going to shrink it by, to keep it all nice and tidy, we're going to have to subtract my boundary amount value by 2 here. That'll keep our math all succinct, and it'll keep our boundary square completely even there. I'll press Control S to save, and let's see if it compiles. Looks like it does. So why don't we go ahead and figure out how to test this guy before we continue on with all the rest of my boundaries within my for loop. So just in my game manager, I'm going to, why don't I just quickly make a void update function, and then do a if input dot get key down key code dot, I don't know, let's say when we press Q, then we're going to call our shrink boundary function, like so. So anytime we press our Q key, we'll call our shrink boundary function. And right now, it should only shrink our right boundary. So a lot of stuff going on here. In our void function, if we press Q on the keyboard, we're calling our shrink boundary function. So that fires this function, and then that fires off this line of code. Then we're launching into a for loop that goes through each of my boundaries inside of this array. We can see my inspector here. And then as we go through my for loop, we check its transform position to see exactly which boundary we're looking at. And then whenever we find the boundary we're looking for, this if statement becomes true. And then we fire off this function, which is our void shrink function right here that actually does the heavy lifting of shrinking our boundaries. So we pass in what object we're currently looking at within our for loop that's going through our array here. And then we actually pass in a new vector that will subtract the position based on how much we want to shrink our playing field by. A lot of steps here, but it's the quickest, it's the most efficient way I've found to do this without having to retype a bunch of different lines of code over and over again. So with that being said, why don't we go ahead and test this guy here. I'm pressing Q and nothing's happening. Well, why don't we go ahead and update my boundary amount by 1 unit. So now that I have a boundary amount, we can see that my right boundary keeps shrinking. And there it goes, it disappears. And this boundary amount can be changed to anything. It can be changed to 0.2. And that'll make my shrink more subtle, like so. So we got a good thing going on now. Now all we have to do is just call my shrink function for each one of my if statements that pertains to each one of my 4 boundaries here. So I'm just going to copy and paste the same shrink call right here, and all I have to do is update my vector over here. So for my left boundary, let's look at my left boundary right here. Now you know why these comments are so handy. Now that I know now I know which if statement pertains to which boundary that I'm needing to solve for right now. All right, so this is a pretty easy one. All we have to do for left is make my boundary amount negative, and that'll shrink it from left to right. What I have to do for my z's is I have to change the boundary amount to a totally separate position. I'm going to leave my x alone and my y alone in my top and bottoms. What I want to update now is my z axis within this new parameter. So same thing down here, just cut and pasting. And since this is the bottom, it needs to have the negative boundary amount. And that should be how we call all of our functions, our shrink function right here. Notice all we're doing with this new vector is just changing how we treat the x, y, and z according to our boundary amount. So in our right one, we're just moving our x position positive in the boundary amount position, and then on our left one, we're looking at the x position, but we're subtracting it negatively, so we're almost like bringing it in. So that's all we really have to pay attention to for each one of these. All right, so now when I press play, with all 4 of my calls, all 4 of my if statements rather, calling the shrink function, and with the right kind of math, I'm getting a shrinking playing field here. So the next thing we're going to have to tackle is how do I keep my player inside of my shrinking boundary. That'll be the next video, how we can keep our player from going outside of my boundary. And then look at this. If it shrinks too much, it can actually shrink on top of my player and then over it. So not only do we have to keep the player within the boundary, but we also have to update the player's position. If he's along the border and it shrinks down, it needs to push him with the shrinking of the boundary. So he keeps staying inside here. And he's getting that. I don't know, that tension that's constantly pushing him in closer and confining him within this play space. All right, thanks for watching.